Okay, so all right, we said quotient rule, right? There's my f function, there's my g function, f prime g minus f g prime. All over g squared. G prime, the derivative of e to the t is just e to the t times 1. All over denominator squared, e to the t squared. Same thing as e to the 2t. Oh, sorry. Do a little bit of cleanup. And then we're just trying to see if we can make our answer look like the cleaned up version that they have. Here we can take out a GCF or a factor of e to the t. E to the 2t. One of them will cancel out. So now we're left with 2 minus 2t over e to the t, and that matches what we want. Okay, so we have our matching velocity function. All right, questions there? Part B, it says show that acceleration is 2t minus 4 over e to the t. So how do we get to acceleration? Find the what? Yeah, find the derivative of velocity. Okay, so we're going to start here, and we're going to try to move to here. So we're not doing quotient rule for here. This is going to be our end goal. So we're going to start here and move towards acceleration. Okay, so a of t. So now we'll let this be the f, and we'll let this denominator be the g. Okay, quotient rule again, right? Numerator and denominator. F prime, 2 minus 2t becomes what? Just -2. G function, no changes. Back to f. And then g prime, e to the t becomes e to the t times 1. All over denominator squared. Okay, we will clean up, and as we clean up, we should be able to make it look like this. That's our goal. We want our answer to look like, our acceleration to be cleaned up to look like that. Combine like terms. These two can combine. -2 minus 2 is -4, -4 e to the t. What can I factor out from the numerator here? Yeah, e to the t, right? I mean, we could factor out 2 as well, but looks like it's not really needing it to be factored out. We just want that e to the t to cancel out. So I get -4 plus 2t, which is the same thing as what is shown. Remove one of the e to the t's out, and we have a match. Right? -4 plus 2t, or 2t minus 4 over e to the t. All right, let's go to part C. Part C says, for what value of t is the particle at rest? So particle at rest, how do we go from there? What does that mean? Yeah. Particles at rest is when you're not moving. And if you're not moving, that's velocity is 0. So that's what we're doing, saying velocity equals 0. But here in this case, there's a numerator and denominator. What do we do? Do we set both equal to 0? Just the top, just the bottom? What do you guys think? Okay, it's going to be just the top. Okay, if we set the denominator equal to 0, then we're looking for where velocity is undefined. That's not the same thing as velocity is equal to 0. So, but I guess it's kind of a moot point because in this case, the e to the t function is always going to be positive. So even if we look for it in the denominator, we're not going to find any in this case. But generally speaking, velocity is equal to 0. If there's a numerator denominator, you're just going to look at the numerator. Solve for t. We get t equals 1. Okay. And it doesn't ask for reasoning, but if it did, then it'll be because v of t is equal to 0. Part D, for the value found in part C, which we know to be t equals 1, is the particle located to the right or to the left of the origin? So we just have to figure out where is this particle located, right? So we'll insert t into the position function and figure out what it gives us, right? If it's positive, then we know it's to the right of the origin. If it's negative, we know it's to the left of the origin. Two times 1 over e to the first power. 2 over e, that's a positive number. So a positive number means particle is located to the right of the origin. Okay, next part, part E. For the same value from part C, is the velocity increasing or decreasing? So do you guys remember from this from chapter 2? How do we interpret velocity increasing or decreasing? Good, acceleration, right? We don't look at velocity. We don't compare signs between velocity and acceleration. This is just acceleration. So let me talk about why that's the case. You see the word velocity. I know it's tempting to just look at the sign for velocity, but you see that word increase, decreasing? That's changing what it's really asking about. It's really asking about the rate of change of velocity. Rate of change of velocity, that's basically the slope of velocity. The slope of velocity is acceleration. So we're just looking at acceleration. Okay. But it's easy to be thrown off because you see that word velocity, so why not use velocity, right? But this description changes everything. Okay, so we just look at acceleration. So rate of change of velocity is acceleration only. All right, so acceleration at 1. So we take 1, insert it into acceleration, we get 2 minus 4 over e to the first power. That's going to get us negative 2 over e, which is less than 0. So we know velocity is decreasing. Because acceleration is less than 0. Okay, any questions there? Okay, for part F, I'm not going to ask us about acceleration, increase, and decrease. That's really the third derivative, so you won't see problems like this. Let me cross that out. Let's ask this instead. For what value of t is acceleration equal to 0? So all we need to do is set acceleration equal to 0. Again, numerator only. We only care about the numerator. Denominator is not going to give us that information. Part G, what is the velocity when acceleration is 0? Okay, so we know that acceleration is 0 at t equals 2, so then we can just find the velocity at 2, right? Okay. Part H is the velocity of the particle increasing or decreasing at t equals 3. Same process as E, right? Wording is exactly the same, just a different t value. We're relying just on acceleration here. Okay. Here, acceleration is positive, so we know velocity is increasing. Right? Okay, for part I, at t equals 3, is the speed of the particle increasing or decreasing? I know the wording looks a lot like H and E, but this one little word is changing how we are approaching this problem. How do we determine if the speed is increasing or decreasing? What do we look at? Between, do we look at velocity? Do we look at acceleration? Do we just one, or do you guys remember? Both, okay. And what would indicate speed increasing? Both of them positive or both of them negative, right? Same signs, right? But if one is positive and the other is negative, that means speed is decreasing, okay? But either way, we're going to have to rely on both velocity and acceleration. But part H and E, we're only relying on acceleration, right? So, you know, that one little word is changing how we're approaching this problem, okay? So we already have acceleration at 3, so we already know it's positive, so we can just gather information from velocity and then we can make our conclusion. So velocity at 3. So my velocity is negative. Acceleration is positive. What conclusion can we make? Speed is what? Speed is decreasing, right? One is positive, the other is negative. Different signs, okay? Okay, for part J, any questions there for part I? Okay. Make sure we include the reasoning as well. For part J, for what value of t is the particle located at the origin? So at the origin, that just means where x of t is 0. So we set x of t equal to 0. And it's just going to be the numerator, okay? If we set the denominator equal to 0, then we're looking for where the position is undefined, and that's not quite what we want, so just the numerator. So at t equals 0, the particle is going to be at the origin. So it looks like this particle is starting at the origin and then moving from there. Any questions? Okay, if you guys can turn to page 13. Page 13, I included a full worked out problem for a curve sketching, but I like for us to work on this from scratch. So if you guys have a fresh sheet of paper, we're going to work through it together from scratch so we can kind of see. But it's nice to have that just in front of you so you kind of check the progress, but we want to walk through this step by step. This is a similar problem from what you're going to see on the test. So page 13. Find relative extrema, POI for y equals x over natural log of x. So relative extrema, we have to define f prime. find critical points, populate sign line. Okay, so let's start that process here. Okay, so I want to find y prime, or I call it f prime, doesn't matter. What rule, what's involved here if I want to find the derivative? Quotient rule, okay? F prime g minus f g prime all over g squared. Okay, step by step here, f prime becomes what? 1. G function, no changes. Back to f. Okay, what's g prime? All over denominator squared. Make sure that we're not just squaring the x, we're squaring the entire function, so make sure to put that in parentheses. Okay, this is not expandable, okay? There's not going to be a log expansion. This is kind of, it's not just the x that's squared, it's the entire function. Okay, let's do a little bit of cleanup. Natural log of x minus, you see that x over x can reduce to 1, so it's natural log of x minus 1 all over natural log of x squared. Okay. There's our f prime. From f prime, we're going to find critical points. Critical points comes from both the numerator and denominator. Okay, so we'll set both equal to 0 separately. Okay, do this one first. Natural log of x equals 1. Okay, it's important that we memorize the natural log graph. When is natural log of x equal to 1? When x is what? E. Okay. You can also solve this algebraically, because if I want to solve for x, I want to get that x out from under natural log. If I involve the inverse, which is base e, I can get those two to go away. We know e and natural log cancel each other out. X equals e to the first power, which is the same thing as x equals e. Okay, so that's a critical point. That's going to have to go on to our sign line. Next up, natural log of x squared equals 0. If I take the square root of both sides, when is natural log equal to 0? When x equals what? 1. So by looking at the graph, or algebraically, this also can be done. Raise both sides, base e. The natural log goes away. X equals e to the 0 power. Anything to the 0 power is 1. Okay, we have our critical points. We're going to place them onto our sign line. There's another restriction that I haven't talked about with this problem, is that natural log has to exist where? It can only take what? Where does the graph exist? Only in the, when x is positive, right? There's no negative for natural log. Natural log of negative is not going to, just doesn't exist. So we know there's already a natural domain issue that the graph has to start at 0. It's never going to be to the left of 0. So I'm going to start at 0 and move to the right. So I know 1 in E. Okay, I'm going to test my information with the derivative function, but I want to choose values in each interval. Here, I'm going to choose 1/2. You know, E is around 2.7, so I can choose 2. And then E, to the right of E, I can choose 3 or 4. But this is what I would suggest. If you can represent values in terms of E, it just makes it easier to pull values without having to do like calculations. So I'm going to choose E squared because I know that E squared is going to have an easy way of cleaning itself up when merged with natural log. So let's talk about how we can interpret these values here. So natural log of, we'll insert 1/2 in for x. We get natural log of 1/2 minus 1 over natural log of 1/2 squared. Denominator is always going to be what? Squared, so it's always positive. So don't have to worry about that. Denominator, just the numerator is going to give us the sign that we want. Okay, natural log of 1/2. What do you know about natural log of 1/2? You don't have a calculator, so we're kind of relying on this knowledge of this graph here. Negative. Okay, so you have negative minus 1, which is still going to be negative, something like negative 0.6 or something. So we know that our graph is going to be decreasing in this interval. Okay, how about 2? Plug 2 in for x, natural log of 2 minus 1. What do you know about natural log of 2? What's your ballpark estimation? Yeah, so maybe 0.5, 0.6, right? Some decimal value between 0 and 1. So imagine it was 0.6. 0.6 minus 1, that's negative. Negative or positive is still negative. I do want to give you a different option, though. That perfectly works fine, but another option is I could also choose something in terms of E in this region. Maybe I can call this E to the 1/2. If I insert E to the 1/2, I'll get natural log of E to the 1/2. And what do you know about natural log of E to the 1/2? Pull that 1/2 down. I can just make it 1/2 minus 1. So that works as well. Okay, so 2, or if you can represent things in terms of E, that's nice. But you can also use your knowledge of the graph to help you through. Okay, let's do E squared. E squared in for natural log of x. Power property, bring that 2 down. 2 natural log of E just gives me 2. We know natural log of E is just 1. 2 minus 1 is positive. Okay, what relative extrema can we see here? Relative min, okay, relative min at E. How do I find the full order pair? Back into the original, right? Now I'm looking for location, right? I'm done with the derivative with the slope sign line. Now I want to find a physical location. So back to the original function. So if I insert E in for the original function, I get E over natural log of E. What does that turn out to be? What's natural log of E? Just 1, right? So E over 1, which is just E. So it looks kind of strange here. Order pair is E comma E. Reasoning is because F prime changes from negative to positive. All right, let's see if we can make some progress into the second derivative. So second derivative, we're starting here. We're moving on to the second derivative. What's involved here? Chain and quotient, right? Quotient first, because there's the parentheses is only over the denominator. Okay. Okay, let's see if we can fill this in here. F prime, what's F prime going to be? Just 1 over x times the g function, no changes. Back to f. And then g prime, natural log of x squared, chain rule. Outside portion, inside portion is natural log of x. Okay, outside portion, 2 parentheses to the first power. And then inside portion is 1 over x. All over the denominator squared. Okay, we'll finish this problem tomorrow so we can do the rest of the point of inflection, second derivative concavity sine law.